Welcome back, students. In this video, we're going to cover the concept of lattice energy. So what is lattice energy? Well, let's first talk about what a lattice is, and maybe this will make a little bit more sense. When you and I normally use the word lattice outside of science, we're probably talking about something for our garden or our yard, and it's this wooden lattice that's maybe made of strips of wood that look like that, and then you can plant something on them and then they'll grow up through that lattice. Fundamentally, what the lattice is it's a network, a regular repeating network. And when we apply that term to chemistry, that's the aspect of a lattice that we're talking about. A lattice in chemistry is a regular repeating network within a solid. So let's quickly just write a little definition here. Lattice in chemistry means a regular, and when we say regular, we mean a predictable pattern. So a regular network of chemical species arranged in a repeating pattern in a solid crystal. So, a lattice is a regular network of chemical species, for example, like ions or molecules, that are arranged in a repeating pattern in a solid crystal. So before I fill in these gaps up here, I'm going to sketch what we're talking about. If I have solid sodium chloride, I'm going to represent that as a solid block of these sodium and chloride ions. You getting the idea now that there is a regular repeating pattern to this? And this would actually be three-dimensional. So there would be a block of these. And this regular repeating pattern of these ions would go throughout that solid crystal of sodium chloride. Well, what does it mean to have a lattice energy? Well, a lattice energy is basically the energy that is holding those ions together. It can also be considered the energy required to convert 1 mole of a solid into gaseous form. So if we take 1 mole of this sodium chloride and we wanted to break all of those ions apart, not just to liquefy them, but to break them apart so that they go off as ions alone by themselves, then the energy required to do that would be the lattice energy. It's basically the energy that we have to overcome to break the solid apart. So it's the energy required specifically to convert 1 mole of that solid into gaseous form. Or we could also say the separate particles in the gas state. And specifically, we're dealing with pure solids here. So I'll say, specify pure solid, right? Okay. So the lattice energy, if we take this solid, I'm going to heat it up, and it may go through a liquid phase first, or it may just sublime directly to a gas. But eventually, I want to split it apart And I'll put a little gas phase indicator on each of these separated species. And all that means is they have just split apart from each other, and they are no longer associated with each other. They're off alone by themselves. So the heat required to do that and that's the lattice energy. The lattice energy is the energy required to break the lattice apart. Now, you can imagine that if this were a +2 charged ion, then it would have a stronger attraction to the negative ion next to it. Because the thing that's holding these together is electrostatic attractions. So the larger the ion's charges are, the stronger the attraction force is between them, and therefore the more energy required to break the lattice. So that's what this comment is saying down here. The lattice energy is greater. It's greater lattice energy when the ion charges are greater. And this is a very important thing because it's not intuitive, and less when the ion sizes are greater. And I'll talk more about why we have this distinction here. But it's basically all based on the strength of their electrostatic attractions. What are electrostatic attractions? It's the attraction of a positive and a negative for each other. Okay? So let's unpack this a little bit more. So we have two rules that are going to determine how large, relatively speaking, a lattice energy is. Rule number 1 always wins. And when I say it always wins, I mean rule number 1 will override rule number 2. So you look at rule number 1, and if it tells you which of the species has the largest lattice energy, then rule number 1 has answered the question for us, and we don't look at rule 2. So rule number 1 says when ion charges are greater, the lattice energy is what? If we have larger charges, they're attracted to each other stronger, so it's going to require more energy to separate them, so the lattice energy is also greater. So for example, if I've got a sodium and a chloride versus, say, a barium and an oxide, the sodium chloride is attracted to each other because of the electrostatic attractions between the positive and negative, but if the charges are greater, then the lattice energy is greater. LE, lattice energy, okay? Now, let's say you're comparing two species and the size of the charges are the same in the two species. Then we go on to rule 2, and rule 2 can help us break the tie if we have a tie from rule 1. When ion sizes are greater, the lattice energy is less. So rule 2 only breaks ties. Okay? So as an example, let's take, for example, a lithium and a fluoride ion. And over here we'll take a potassium and a bromide. Okay? Now the lithium is a +1 charge, right? So lithium is +1, fluoride is -1. And the same goes for these. Potassium is +1 and bromide is -1. So rule number 1 does not help us. Rule number 1 won't tell us the difference. in their lattice energies. So we go to rule 2, lithium fluoride and potassium bromide. So we have to think about their relative sizes. So if we take a look at our periodic table, lithium is here compared to potassium down here. So you can see that potassium is much larger than lithium, right? And if we compare fluorine to bromine, we can see that bromine is much larger than fluorine. So if I were going to draw these two, I could draw a lithium and fluoride. Potassium is a lot larger than lithium. So here's a potassium. And then if we go across bromide, or the bromine, so bromine would actually be larger than potassium, and the fluoride would be larger than the lithium, because when the lithium forms its ion, it's lost its N equals 2 energy level. And same thing has happened for the potassium. When it forms an ion, it has lost its N equals 4 valence level. So now I have two examples, and these sizes can kind of give me a rough idea of what's going on. So let's take a look at from the center of that lithium ion to the center of that fluoride ion. And the distance, there's the distance. It's about that length right there, right? And if we do the same over here, potassium bromide, we see that the distance is larger. It's about like that, right? Why is this significant? Well, in physics, when we calculate the strength of electrostatic attractions between charged particles, we typically measure from the center of the charged particle. So this charged particle is considered to be right there. That charged particle is considered to be right there. And so this internuclear distance, the distance between the two nuclei, is larger here because the ion sizes are larger, and it's smaller here because the ion sizes are smaller. So how is that relevant? Well, we know that when we get charged particles very close together, their attractive forces increase. It's like having two magnets close together. And when you have two magnets and you get them closer, you can start to feel a stronger attraction. But if the magnets are further apart from each other, then the attractive force weakens. So that's what's going on here. For smaller ions, their internuclear distance is smaller, which means they are closer together, which means they have a higher attractive force between them. Compared to larger ions, where their internuclear distance is a greater distance, which means the attractive force between the two ions is less. So another way of saying that is, when the ion sizes are larger or greater, the attractive force gets less. And if the attractive force is less, then it takes less energy to break them apart, and therefore the lattice energy is less amount of energy required to break them apart. So here we go. Assuming that the ion sizes are different, and we have already ruled out rule number 1 because the ion charges are the same. We look at the ion sizes, and the ion sizes will help us break a tie. The larger the ions, the less the lattice energy required to break them apart. But again, rule 2 is only used to break ties between the ion charges. If we've already decided that by rule 1, which has the greater lattice energy, then we never have to deal with rule 2. Okay? All right. So here on the rest of the page, I've given you 3 sample problems. Now, sample problem 1 is a straightforward application of Rule 1. Sample problem 2 requires us to use Rule 2 to break the ties because all of the ion charges are the same. And then example problem C requires us to be able to combine both of those principles and see if we can order these when we're using both rules. Before we get started, just want to point out, I want you to rank them in increasing order. What does increasing order of expected lattice energy mean? That means you're getting larger and larger and larger lattice energy. So the greatest lattice energy should come at the end of the line, right? So make sure that you are ranking them correctly. I often see on exams and quizzes where students know exactly what they're doing with regard to lattice energy, but they rank them in opposite order because they've misread the question. So if we are increasing in order, that means we're getting larger and larger and larger lattice energies, right? So go ahead and try all three of those practice problems, and you can pause the video to do so, and when you're done, come on back to the video and then I'll answer these for us. All right, coming back from pausing the video, we're going to answer these three. Example A, rank the following in increasing order, so from smallest to largest, of the expected lattice energy. So I've got lithium fluoride, magnesium oxide, and scandium-3 nitride. Remember, I've got to specify the charge on that scandium because it's variable. So lithium and fluoride, magnesium and oxide, scandium-3, and nitride. How did I know that was a scandium-3? It's paired up with one nitride. The nitride has a -3 on it, so that one scandium must have a +3 on it. Well, you can see right away that the charges are different, aren't they? These have much larger charges. So what does the rule number 1 say? Rule 1 says the larger the charges, the larger the lattice energy. So this is just using rule number 1. So lithium fluoride would come first because it's got the smallest one, and I want to be in increasing order, right? So that's the smallest lattice energy. Magnesium oxide would be the next because they have the next larger charges. And then following that would be scandium-3 nitride. So it just so happened that they were already in the correct order in the problem, but you can never rely on that. Okay? That question only required us to use Rule 1 because Rule 1 was sufficient to answer, which had the greater lattice energy. The species with the greater charges have the greater lattice energy. Moving on to sample problem B, now we are dealing with lithium iodide, sodium iodide, and potassium iodide. So I've got lithium iodide, sodium iodide, and potassium, and then the iodide. Well, notice Rule 1 does not help me here because they all have the same charges. So I cannot apply Rule 1. They all tie in terms of the size of the charges. So now I've got to think about their sizes of these species. And so I'm going to use Rule 2 to break the tie here. Remember, here's lithium, and then the sodium is larger, and potassium is larger. The iodides are all the same size, so I don't need to think about those. The potassium iodide has larger ions. What happens when we have larger ions? The energy becomes less because the ions are further apart from each other, and therefore they have weaker attractions, so it's less energy to break them apart. So the smallest lattice energy is the largest ion. And then the next one would be the sodium iodide. And then the one with the highest lattice energy is the lithium iodide because it's the smallest ion here. Now notice that this example B, it was a fairly straight shot through rule number 1 because that rule number 1 didn't help me. So I went to rule 2, and rule 2, based on the ion sizes, helped me answer the question. Now we get to example C. And example C is a little bit more complicated. So let's see if we can figure this out. So I've got sodium chloride, and sodium and a chloride ion, and calcium chloride. So calcium with a 2+ charge and 2 chlorides, right? And potassium bromide, KBr. All right, so we look at rule 1 first. And rule 1 says the species with the higher charges have the greater lattice energy. So I know right away, right here, all of these others are plus and minus 1s. There's a 2+. That has the highest charge, and so that is going to have the highest lattice energy. If I'm in increasing order, then that one will come last because it's the largest. So that one is at the end of the line because it's the highest lattice energy. That leaves me these other two, sodium chloride and potassium bromide. And rule number 1 is not going to help me decide between those two because they are both same charges. So I go on to rule 2. And I let rule 2 see if it can break the tie. Sodium chloride, potassium bromide. Here's sodium, and here's potassium. So sodium is smaller than potassium. Here's chlorine, here's bromine. So bromine is larger than chlorine. So this potassium bromide, these ions are larger ions and smaller ions. So that's going to help me break the tie. We know that larger ions have weaker lattice energy. So of these two, which has the stronger lattice energy? Sodium chloride does. So it would come here. And the weakest lattice energy of all would be this one. And there we go. We have ranked these species in terms of their increasing lattice energy, the lowest lattice energy up to the strongest or highest lattice energy.